Next up from Chapter 5 is 5.2, calorimetry. Here we're going to explain the technique of calorimetry and calculate and interpret heat and related properties using typical calorimetry data. So first off, what is calorimetry? And it is a method that we use to measure the amount of heat transferred to or from a substance. Okay, so we use this for both chemical and physical processes. And what happens is we're looking at the heat that is exchanged with a calibrated object, aka a calorimeter. And what we do is we look at the change in temperature of the measuring part of the calorimeter, and we can convert that to heat and use our thermochemistry to figure out the heat from whatever it was that we put in the calorimeter. So one of the first things that we need to understand is the difference between a system and surroundings. And you get to determine what your system and surroundings are in this case. So the system is whatever it is that is undergoing the change, the chemical or physical change. And the surroundings are everything around it. Okay, so in the grand scheme of things, the surroundings is all of the universe. But you can also make it so that your surroundings is, for instance, a calorimeter. Okay, and your surroundings either provide the heat to the system or absorb heat from the system. And we'll look at a picture in a second, but the calorimeter itself is the device used to measure the amount of heat involved in a chemical or physical process. So a lot of times these occur in solution, so they occur in water. When we have an exothermic reaction, the heat that's produced is absorbed by the solution and it gets hot. If we have an endothermic reaction, the heat that is required for the reaction to occur is provided by the solution. Okay, so in this case, it gets cold. And when I'm talking what's getting cold is the actual surroundings. So here's some examples of some systems versus surroundings or solutions. Okay, in A, we have an exothermic process. So the system, okay, is the circle in green. And what's happening is this process that's happening, it's getting hot, it's releasing heat. So it has a negative Q for the system, because the heat is leaving the system and going into the surrounding. So the surroundings have an increase in their temperature. So the surroundings have an increase in their Q. Now in B, we have an endothermic process. And so that means that energy is being absorbed by the system. So the surroundings is actually giving its Q, is giving Q to the system. So in this case, our temperature goes down for the surroundings, and our system has a positive Q, has an increase in heat because it's absorbing it, and our solution has a decrease in Q because it's losing. So a little bit more about calorimeters. To start off, they have to be insulated. And this is because you don't want to allow heat to transfer to the outside environment. And you want all the heat exchange to only happen with your little system and the surroundings being your calorimeter. So in the lab, in general chemistry labs, we often use coffee cup calorimeters. And they're literally just that. They're polystyrene cups that are used as our calorimeter. And we have much better ones for industry, research, and then for those of you that might be chemistry majors, when you go on to a 4-year university and you get to physical chemistry or PChem, you'll usually get to experience a bomb calorimeter, which we'll talk about those a little later. So this is what a coffee cup calorimeter tends to look like. Some places use covers, some don't. But you've got some styrofoam cups here. Okay, nice and insulated, and you've got your thermometer and some type of stirrer to stir the solution when you're adding things to it, and you look at how this temperature changes in the thermometer. These are some examples of some commercial calorimeters. An A is kind of a student use, cheaper type one that's a little more, it's much more expensive than a coffee cup one, but still gets the job done. And then we have more expensive ones, but they all have the same type of setup, in that you have some insulation and you have the inner part where your water is, or that's your surroundings, and you have a thermometer that's very precise, and a part to put your solution in. So now let's say we take a hot piece of metal and we put it in some cool water. Okay, so we've got our calorimeter here. It's our cool water. Okay, so there's our cool water, there's our thermometer. And we notice that when we put in this hot piece of metal, that our temperature of our water starts going up until it eventually stops increasing. So what's happening is the metal is giving its heat to the water. So the metal is losing heat and the water is gaining heat from the metal until eventually they reach thermal equilibrium, meaning they are the same temperature. So you would watch that thermometer until it stops moving. So since we're in a calorimeter, one thing we can assume is the heat exchange is only between the metal and the water. So because of that, the net change in heat is 0. Okay? And we can rearrange this, and what we find is that the heat gained, this should be W. I'm going to kind of change things around here. The heat that is gained by the water is equal to the heat lost by the metal. Yeah, you could say it the other way too, but it's more accurate this way because the metal is what's actually losing our heat. Okay, so they're equal in magnitude but opposite in sign. So one is losing heat, one is gaining heat. But the amount one gains is equal to the amount the other loses. So this is just kind of a picture to look at this calorimetry process. We put the hot metal in. We notice that it loses heat, it loses Q, and the thermometer, the temperature starts going up until eventually it stops once they've reached thermal equilibrium. Okay, so we're going to go ahead and do an example where we're able to look at how the Q of the system is equal to the negative Q of the surroundings. And here's an example. This is something kind of like an experiment that you might do in a lab. We take a piece of metal, we drop it into some water, and we watch the water temperature go up, and we want to figure out what the initial temperature is of this metal. So one thing that we can write down right away is that the energy that the rebar lost is equal to the energy that the water gained. Well, we can rewrite this as the energy the rebar gained is equal to the energy the water lost. It doesn't matter. Now we know that Q equals MC delta T. So we can rewrite these equations to say mass of the rebar times specific heat of the rebar times the change in temperature of the rebar is equal to the negative mass of the water times specific heat of the water times the change in temperature of the water. So now let's go ahead and get this delta T rebar by itself, because we're looking for the initial temperature of the rebar. So we can divide both sides by mass of the rebar times specific heat of the rebar. And we see that delta T of our rebar is equal to negative mass of the water times specific heat of the water times change in temperature of the water divided by the mass of the rebar times specific heat of the rebar. Now delta T is equal to our final temperature minus our initial temperature. Okay, so to get T initial by itself, we know that a negative T initial is equal to negative MW CW delta TW over MR CR minus T final. And we need to multiply everything times a -1 to make this positive. So T initial is equal to positive MW CW delta TW for MR CR plus T final. Okay, so let's go ahead really quick and calculate the delta T of our water. It's final minus initial. And the final temperature is 42.7 degrees Celsius minus the initial at 24.0. And we get that the change in temperature of our water is equal to 18.7 degrees Celsius. Now let's also go ahead and write down what else we know. Our final temperature, this should say rebar. The final temperature of our rebar is the same as the final temperature of the water because it goes to thermal equilibrium. So this is where the temperature stopped changing. So they have the same final temperature of 42.7 degrees Celsius. Okay, everything else is pretty much given. The mass of our water is, we're told it's 425 milliliters. And we know the density of water, there's 1 gram of water per 1 milliliter. So we have 425 grams of water. The specific heat of water, we can look that up. It's 4.184 joules per gram degree Celsius. And we have our delta T already. The mass of our rebar was given to us at 360 grams. And we were told for the specific heat of the rebar to assume it's steel, and it basically has the same specific heat of iron. And so that is equal to 0.449 joules per gram degree Celsius. So now we can plug all that into our equation. 425 grams times 4.184 joules per gram degree Celsius times 18.7 degrees Celsius divided by 360 grams times 0.449 joules per gram degree Celsius. We can see units canceling out, plus 42.7 degrees Celsius. So you can see from the bigger part of the equation, we're left with degrees Celsius to add that to 42.7. Now we're going to punch all this into our calculator. And we get an initial temperature of 248 degrees Celsius. Now another way you can do this is how your book does it, and it'll go through the steps too in the next couple slides. But another way you can do this, I'm just going to go ahead and clear the ink on the slide and kind of start over, is you do know, same thing, that Q of the rebar is equal to the negative Q of the water. And you can first solve for the Q of water, because that maybe it's a little easier that way, because you write down what we know, and we know that we're automatically told the mass of the water. We can figure that out from the volume, 425 milliliters, 1 gram per milliliter, 425 grams. We know the specific heat of the water is 4.184 joules per gram degree Celsius. Delta T of the water we can solve. It's 42.7 degrees Celsius minus 24 degrees Celsius. And it's 18.7. And so then we can solve for our Q of the water. MC delta T. Notice this is basically the first half of the numerator from what we did the first way we solved this. And we get that the heat from the water that the water absorbed is 33,252 joules. And it's normal for it to be a big value like that, because joules are very, very small. So now we have a Q, this is equal to negative QR. So now we have Q for our rebar. We know a mass of the rebar. We have a mass of 360 grams. We're told it's the specific heat of iron, which is 0.449 joules per gram degree Celsius. And then delta T, though, we know is T final minus T initial. We don't know T initial, but we know T final has the same final temperature as the water, 42.7 minus T initial. So now we know Q equals MC delta T. Getting delta T by itself, delta T is equal to Q over M times C. T final minus T initial equals Q over MC. Negative T initial is equal to Q over MC minus T final, and multiplying everything by -1. T initial is equal to negative Q over MC plus T final. So now we know that our Q of the rebar is equal to negative QW. So, plugging and chugging, negative from our formula for T initial, negative 33,252 joules, divided by the mass, 360 grams, times specific heat, 0.449 joules per gram degree Celsius, plus final temperature, 42.7 degrees Celsius. And we get the exact same answer. So whatever method is easier for you is perfectly fine. It's all the same. I just wanted to show you this way, because this is actually the way that when you're in a lab you might do it. While you would still do it, I mean, the math is all the same basically, but sometimes you have a lab manual that wants you to walk through the steps, wants you to walk through it step by step, where you're putting in your data step by step. So again, they went ahead, this is the exact same way we did it. Your book also, actually, let me go to a blank slide here. Okay. Your book also gives another example where, and this is a little bit more common to do in the lab, where you use specific heat to identify a metal. So we're told we have a 59.7 gram piece of metal that we put in boiling water. Virgin boiling water. Okay, and then it was transferred into 60 milliliters of, whoops, no, I hate when it does that. Okay, 59.7 gram metal in boiling water. Quickly transferred into 60 milliliters of water initially at 22 degrees Celsius. Final temperature of the water was 28.5 degrees Celsius. And we want to find the specific heat of the metal. Okay? And then use that result to identify it. So the first thing we should probably do is write down what we're given here. So the mass of our metal, we're told, is 59.7 grams. And we're actually told its initial temperature. We're told that it was first in boiling water. So that means that the metal was heated up. That boiling water is not the calorimeter. So in a lab, this is what we would do. You heat it up in the boiling water to get it really, really hot, and then you know what the temperature is because it's the same as the temperature of the water. So that means the initial temperature of our metal is equal to that of boiling water, and water boils at 100 degrees Celsius. And then we know the final temperature of the metal as well because it's equal to the final temperature of the water it was transferred into that was allowed to reach thermal equilibrium. So that is 28.5 degrees Celsius. We don't know its specific heat, so that's all we know for the metal. For the water, the mass of our water, we're told we have 60 milliliters, and then we can make that into grams using density. So we have 60.0 grams of water. We're told the initial temperature of our water is 22 degrees Celsius. And our final temperature of our water is 28.5 degrees Celsius. And we know this is water, so the specific heat of our water is 4.184 joules per gram degrees Celsius. So like before, we know that the Q of our metal is equal to the negative Q of our water. So let's go ahead and do it the second way that I showed you, where we go ahead and find the Q of water first. Q water equals MC delta T of water. So that is equal to 60 grams times 4.184 joules per gram degrees Celsius times our change in temperature, which is 28.5 minus 22.0. That's 6.5 degrees Celsius. 4.184 times 60. And this Q is equal to 1,631 joules. And so now that is equal to the Q of our metal. And so for our metal, we know that QM, whoa, okay, pen, equals MC delta T. And we need C, so we're going to divide both sides by M delta T. So our specific heat of our metal is equal to QM over mass of the metal times the change in temperature of the metal. And so we have negative, since this is negative Q metal. So now we have negative 1,631 joules divided by the mass of our metal, 59.7 grams, times the change in temperature. Now our final temperature is lower than our initial, so we have 28.5 minus 100 degrees. So this is negative 1,631 joules divided by 59.7 grams times negative 71.5 degrees Celsius. Punch this in. And we get 0.382 joules per... Oh, I'm running out of room over here. 0.382 joules per gram degrees Celsius. And technically it should be 2 sig figs, so 0.38 joules per gram degree Celsius. Because of this 6.5, that's 2 sig figs. So then this should have been changed to 2 sig figs and so on and so forth. I'm not going to worry about that right now. We're just solving for this. So now we have our specific heat. And then we go ahead and look at the table 5.1, and we see that the specific heat of copper is equal to 0.39 joules per gram degree Celsius. So the metal is probably copper, since that's what it's closest to. And in the real world, if you were given a piece of copper, you would know it's copper because of its color. But still. If you want to do this kind of how the book does it, where they put everything in one big equation, it is there on page 247. All right, so like we said, the reaction heat is equal to the negative solution heat. The amount that one produces is equal to the negative amount of the other absorbed. And this is really what is the heart of all calorimetry problems. So here's an example doing this with an actual chemical reaction. So we're told 50 milliliters of a 1 molar hydrochloric acid solution and 50 milliliters of a 1 molar sodium hydroxide solution at 22 degrees Celsius are put in a coffee cup calorimeter. Temperature reaches a maximum of 28.9 degrees Celsius. What is the approximate amount of heat produced by this reaction? And they give us the balance reaction also, which there really isn't anything to do to balance it. So first, think that you're combining these solutions so quickly that there's no reaction taking place until they're mixed. Okay, so don't be like, okay, they're going to start reacting as soon as they start combining. In reality, that's what happens, but this is general chemistry. We're going to pretend it doesn't. Okay, so while they're mixing, okay, before they're completely mixed, you have a 100 milliliter solution of both hydrochloric acid and sodium hydroxide. And then once they're mixed, then they react to get it to 28.9 degrees Celsius. So using those assumptions, then we can go ahead and use that the heat of the reaction is equal to the negative heat of the solution. This is assuming that the calorimeter is not absorbing any heat, and there's no heat exchange between the calorimeter and the environment. Lots and lots of assumptions. Nonetheless, we can go ahead and figure out, we know that the heat of our solution is equal to MC delta T of the solution. So we got to make some more assumptions. The solution is aqueous, So we're going to proceed as if it basically is water in terms of its specific heat and density. And that's honestly a pretty safe assumption to make. 1 molar sodium hydroxide hydrochloric acid, that's really not going to do much as far as changing the density or the specific heat of the water. So since we now have a total of 100 milliliters, since we mixed the 50 and 50 milliliters of the solutions, then we have a mass of 100 grams. And then we can go ahead and use the specific heat of water. And so then we get this, that the Q of the solution is basically that of water. Okay, water specific heat, water mass, and change in temperature of the water. And then since we actually want the heat of the reaction, not of the solution, remember it's the negative of the solution, so it's negative 2.9 times 10 to the third power. So this is an exothermic reaction. When you mix acid and base together, they create heat. And this ends up being 2.9 kilojoules of heat that is released. So the reason we actually don't say it produces negative 2.9 kilojoules of heat is because we're saying, by saying the reaction produces heat, that's saying it's released. Okay, so it's basically saying the negative without saying negative 2.9. It's just, we're saying negative in a different way. So if you've ever seen a chemical hand warmer, for a while they were having these in like grocery stores. They would do these like giveaways. You get like a chamois if you went and watched a little demo in the store, or they took this hand warmer and they showed you how they make this little metal thing snap, and then all of a sudden it crystallizes. It gets hard and hot, and then all you do is put it in boiling water, and it's back to being reusable. And this is how they work. They have a metal disc, and what happens is when you make that disc snap, it's transferring some energy into the solution, and this is called a supersaturated solution. I know all about those from grad school. So what that means, we talked a little bit about solutions. So there's actually more than should be allowed to be dissolved in water here. But it's chillin', but just any little bit of a disturbance is going to make it precipitate out of solution, all the extra that shouldn't be dissolved. Okay, so when you snap that little metal disc, you're giving it that energy for it to be like, wait, I don't want to be in solution anymore. So then it starts to nucleate, basically, and as some more and more comes out of solution, then it's like, hey, the stuff that's dissolved wants to keep sticking and sticking. So then it becomes this nice, big, hot, hard heat pack. And then you put them in boiling water and you redissolve that compound. And it's actually sodium acetate is the compound. So this is NaC2, I don't know why my pen keeps doing these weird things. NaC2H3O2. Aqueous, becoming NaC2H3O2 solid. And technically plus heat, if you will, you can use the delta to mean heat. So it's exothermic, it's releasing heat. Another example of a hand warmer are the ones like the TheraPaks, where they're in plastic, and then you rip open the plastic, and what happens then, you're exposing it to air, and it has iron in it, and so that iron then reacts with oxygen gas in the air to make iron 3 oxide, and this is a very exothermic reaction, so it produces heat. But this is also why those heat packs sometimes take like 30 minutes to get hot, because you have to let the reaction happen long enough to make enough heat to actually feel it. I talked a little bit about instant cold packs before. You have ammonium nitrate and then a bag of water. you break the bag of water, and the ammonium nitrate, when it's dissolving in water, it's actually an endothermic process, so it's absorbing energy from its surroundings. And then it gets cold, and when you feel that cold, what's happening is your body is giving the heat to the cold pack. So it's absorbing your body heat. Okay, so let's talk about bomb calorimeters. They're not actually bombs. Chemists are just freaking weird. Just basically called that because of how they look. But so these are used to measure the energy produced by reactions that give a lot of heat in gaseous products. So things like combustion reactions. When I took physical chemistry or PChem, we got to use a bomb calorimeter. It was pretty cool. So you have this really strong steel container that has the reactants, and the container itself is in water. And the energy produced by the reaction is trapped in the bomb and then the water. So you have a little bit more that you have to do in terms of calculations. But this is an example of one. The actual bomb, if you will, is right here, and then it's got the water around it, and then you've got another container, and then you've got even more containing it to make sure everything stays in it and is nice and insulated. We also have whole body calorimeters, and these are big ass calorimeters that can hold a human being in them. So these are used for measuring things like metabolism of people under different conditions, like environmental conditions, dietary regimes, or health conditions. And this is where, again, the nutritional calorie comes into play with the capital C. Let's see the example I want here. No, okay. Back to a blank slide and another example. So I want to go through a bomb calorimetry example. And we're told we have we have 3.12 grams of glucose, which is C6H12O6. And we're putting that in a bomb calorimeter. And the temperature of the calorimeter increases from an initial temperature of 23.8 degrees Celsius to a final temperature of 35.6 degrees Celsius. We're told the calorimeter contains 775 grams of water, and the specific heat of the actual calorimeter, the bomb calorimeter, has a specific heat capacity of 893 joules per gram degree Celsius. And we want to know the amount of heat produced by the combustion of the glucose sample. So notice that the combustion is absorbed by the water and the bomb. It's not just the water here. Okay? So that means that the heat from our reaction, okay, is still equal to the negative heat of the surroundings. But in this case, our surroundings, my cat Dexter says hi. Our heat of the surroundings is equal to the negative heat from the water and the heat from the bomb. Oh, Dexter. He's 12 years old and he has an attitude and wants everyone to know that he's beautiful and should be the center of attention. Okay, so we can figure out our heat for the water and the heat of the bomb. So let's look at this. The calorimeter is not joules per gram degree Celsius, it's just joules per degree Celsius. So that was a little mistake on my part. Okay, so our Q of the water equals MC delta T. So we have 775 grams times 4.184 joules per gram degree Celsius times our temperature change, 35.6 degrees Celsius minus 23.8 degrees Celsius. And let me check that again. Okay, so that's 38,263 joules. And our Q for the bomb. Now, we're given C in terms of joules per degree Celsius. We're not even worrying about the mass here because it's already incorporated into the specific, or not specific heat, it's just the heat. Okay, so this is a big capital C. This is the heat capacity of the bomb. So then that's equal to our heat capacity of 893 joules per degree Celsius times the change in temperature. Now it has the same change in temperature of 35.6 minus 23.8 degrees Celsius. And so this is equal to 10,537 joules. I'm going to worry about sig figs for the very end. So now the Q of our surroundings is equal to the sum of those, 38,263 plus 10,537 joules. And this comes out to 48,800 joules. And so our Q of the reaction is equal to negative Q surround. So that means it's negative 48,800 joules. And if we want to change this to kilojoules, just to make it look a little prettier, 1 kilojoule per 1,000 joules, we get negative 48.8 kilojoules. So we could also say that 48.8 kilojoules of energy are released. Oops. Well, that's gone now. But 48.8 kilojoules are released when 3.12 grams of glucose was burned. This is also an exothermic reaction because it is a negative Q, meaning the energy leaves the system, or leaves the surroundings, enters the system. Okay, so just kind of a quick little thing when it comes to nutritional calories. When you're looking at a nutrition facts label, it tells you your calories, and remember those are kcals. And you know you can actually calculate the approximate calories even if you're not told what the calories are in a serving. Because there's actually, for every gram of protein, so for protein, there are 4 kcal for every 1 gram. For fat, there are also 4 kcals, or big calories per gram. Or not fat, sorry. That should be carbs. And fat contains 9 kilocalories for every 1 gram. So you can take the information from the lower part of your nutrition facts for protein, carbs, and fats using the totals and calculate your calories.